In this chapter, we introduce the concepts of solid-state physics that were introduced after the advent of quantum mechanics. We start with the quantum mechanical description of bonding in a simple molecule. We will be looking to see how the electronic wave functions change from atomic orbitals to molecular orbitals. We start with a simple diatomic molecule, the hydrogen molecule, represented by two hydrogen atoms separated by a small distance. The potential energy of this system is the Coulombic potential of the isolated atoms, added together, where the region that makes the most difference is the region between the atoms. We start by considering the case when the atoms are so far apart that the ground state wave function would have to tunnel to go from one atom to the next. In this case, we expect that the wave function to be very small in the tunneling region, which is the only region affected by the interaction. Thus, we expect the electronic wave function psi to look almost identical to the atomic wave function. Here, we'll draw them like 1s wave functions. Now let's consider the case where the atoms are closer together, such that the electron doesn't have to tunnel to go from one atom to the next. In this case, the electron is still confined, but it's confined in a larger box, the size of two atoms. From our experience with particle in a box, we can expect that the lowest energy or ground state wave function should always be positive, never crossing zero, with no nodes in it. Because the potential is still very similar to that of an isolated atom, we start by expecting that the wave function looks an awful lot like that of an atomic wave function. For the region in between, we will make sure that the wave function simply stays positive, not crossing zero in the middle. This wave function we have just described spreads across the entire molecule, and so we'll call this a molecular orbital. Recall that the energy of the ground state wave function for a particle in a box depends on the size of the box, such that if we increase the size of our box, the energy of that wave function should decrease. Thus, the energy of this molecular orbital is actually less than the energy of the atomic orbital, which we used as a basis to draw that wave function. Now, we can also expect from our experience with particle in a box that the first excited state is the next largest wave function to fit within the box, having a node at the center. Again, the wave function should look similar to an atomic orbital because the potential is very similar to that of an atom. The energy of this wave function should be slightly higher than that of the atomic orbital or this lower energy orbital because the wave function is ever so slightly more curvy in this intermediate region. These two molecular orbitals we have just rationalized are known as the bonding and antibonding orbitals. We can use this approach we just described to develop a very good quantitative model for the wave function of these molecular orbitals. We start with the exact atomic orbital wave functions that we derived for isolated atoms. Then we consider these wave functions centered at the position of the two different atoms. When r, the distance between the two atoms, is very large, we simply have two states at the same energy. When the two atoms are brought close together, we can approximate the wave function of our bonding molecular orbital as the sum of the two individual atomic orbitals centered at A and B. We could have also chose the antisymmetric configuration of the molecular orbital, giving us a node in the middle. Although for this one, we will recognize this should have higher energy than the symmetric contribution that doesn't have a node in the middle. In general, when we start with two atomic states, we will expect to have two molecular states as a result. Each of these molecular orbitals, like an individual atomic orbital, can contain two electrons spin paired. In the case of hydrogen with only one electron per atom, that means the lower energy bonding molecular orbital can accommodate both electrons in a spin paired configuration, while the antisymmetric antibonding molecular orbital contains no electrons. This example of forming a more complicated wave function out of the summation of simple atomic orbitals is a simple example of using a linear combination of atomic orbitals that we will use throughout the rest of this course. In general, we will use the various atomic orbitals centered at different atoms as a basis to produce more complex molecular orbitals. We form different molecular orbitals by combining the atomic orbitals with different sign or phase, and we expect the number of independent molecular orbitals to be equal to the number of atomic orbitals in our basis. Now let us consider where the electrons go in the bonding and antibonding orbitals by considering the square of the wave function, which gives us the electron probability distribution function. In the case of the bonding orbital, where the wave function was always positive, the probability distribution looks similar, where the region between the two atoms has significant electron density. On a contour map, this is shown as a merging of the electron density into a single unit, and one can imagine that all of this negative charge in between the positively charged cores is adding to the attraction between the two atoms. In the antisymmetric antibonding orbital, squaring the probability density gives a symmetric function, but the wave function node results in zero electron density in the region between the two atoms. The contours of electron density in this case look like the atoms are repelling each other, and in fact, because there is no electron density in the region between, the positively charged atoms actually do repel each other more than would exist in the bonding case. Now let's consider the energy of the molecular orbitals as a function of R, the interatomic separation between the two atoms. When R equals infinity, the molecular orbitals are exactly the same as the atomic orbitals, and so the energies are the same as the atomic energies. As the separation decreases, the energy of the bonding orbital decreases because the effective size of the box increases, whereas the antibonding orbital's energy increases because the wave function becomes slightly more wiggly. At very low interatomic separations, where the two atoms are essentially right on top of each other, the Pauli exclusion principle will raise the energy of both of those wave functions, which then makes a minimum in energy for the bonding molecular orbital at some equilibrium distance A. Keep in mind that we started with two atomic states, each with one electron for a hydrogen atom, that then splits into two molecular orbitals, a antibonding and a bonding state, where the bonding state can accommodate both of those electrons. This leads to a net bonding energy given by the difference of the starting atomic orbital and the resulting energy of the bonding molecular orbital. We often diagram the change in energy of the electronic states in this way, where we start with the energy of the atomic orbital for each of the two atoms before the interaction, and then when the atoms come together to form the molecule, we show the bonding molecular orbital with a reduction in energy from the two atomic states, and then the antibonding orbital with an increase in energy. For a hydrogen atom, we have only one electron in the 1s electron state, but then when we form the bonding molecular orbital, that orbital can handle the electrons from both the hydrogen atoms, making a filled spin paired molecular orbital and then a completely empty antibonding orbital, such that the net energy of bonding for each electron is this difference between the atomic state and the bonding molecular orbital state. Notice that the increase in energy of the antibonding orbital is slightly larger than the decrease in energy from the bonding orbital, such that a net bonding energy only occurs if the antibonding orbital is empty. If we had, for example, helium atoms instead of hydrogen atoms with two electrons in the 1s orbital, both the bonding and antibonding orbitals of the molecular orbital system would be filled, each with two electrons in the molecular orbital. Because this increase in energy from antibonding is actually larger than the decrease in energy from bonding, the overall effect of the entire system is such that the bonding interaction has higher energy than the individual atoms. In this way, helium atoms prefer to be isolated atoms rather than bonded into a diatomic molecule. The general theme here is that bonding only happens when orbitals overlap that are partially filled. For example, hydrogen with only one half-filled 1s orbital and fluorine with only one half-filled p orbital, the other p orbitals being completely filled, form an interaction of bonding and antibonding such that the bonding orbital becomes entirely filled and then the antibonding orbital is empty. This explains the single covalent bond in the HF molecule.